So what we are going to cover today are as follow: some brief overview of differential analysis, and then we will go through the structure of my GPU accelerated algorithm for differential cluster search. So I will introduce the something you need to know about GPU if you don't know about that yet. Then I will go through the baseline CPU algorithm that I use for comparing our GPU accelerated algorithm to the CPU baseline algorithm. So the same baseline CPU algorithm is also used for generating the differential to be used during our differential cluster search as well. Then, since our approach is also make use of meet in the middles, I also introduced the meet in the middle approach so that it is kind of more clear on what we are trying to do during the meet in the middle sessions. Then, with all of this combined, we are only ready to look at the GPU algorithm framework. I will also cover some implementation aspect of the GPU algorithm for differential cluster search. I will talk about memory allocation, minimizing branch divergence, as well as maximizing GPU occupancy. Then finally, I will try to go through my code with you all so that you know which part of the code correspond to what, and maybe on how to begin on modifying my code toward adapting toward different block cipher, hopefully. So that is the plan for today. So this is just the basics. Let's go through it very quickly. So we are going to do the differential cluster search on our block cipher. Here, a block cipher is defined as the encryptions of symmetric encryption using the same key for encryption and decryptions, and it operates on a fixed set size of data in a block unit. Its main function is, of course, to encrypt and decrypt the data to protect the confidentiality of our data. Then this is how our block cipher look like. First, you have a plain text box, and then after you pass it through our block cipher encryption algorithms together with the secret key, it will produce the ciphertext block. So it's a straightforward process. Go through the algorithm encryptions, take in the secret key together with it, and go through it together, and we got our ciphertext block. Then to obtain back the plain text, we go through the same process, but in reverse. We start from ciphertext block, then we go through the encryption algorithm, but it's called decryption now, the decryption algorithm, together with our secret key to produce the plain text box. So inside the algorithm itself, the encryption decryption algorithm, or we call the block cipher, here we actually composing our block cipher using a number of similar round functions. Here R0, R1, R2, R3 until R-1 are usually the same functions for our block cipher. And then they're using the same structure. The only different thing might only be the different subkey that is provided toward individual different round. So with a rough idea of what block cipher is, a differential analysis will analyze the central structure of our block cipher. What it does is, first of all, you have a plain text here, and then you have a ciphertext here, right? So what if you have a pair of them and then XOR them together? What you get is a XOR difference, which what we use in different.
Hello, Yeoh.
Yeah.
Just a moment. Your slides did not change.
It still start on first page.
Yeah. Now, okay. Now it just changed. Yeah. Okay. Yeah. Thank you.
Wait. If I scroll it now, did it change? I changed the slide. Did it change on your side?
No, it's not changing on our side.
Wait. Or maybe I need to start it first, then only I share. All right, did it change to the first page?
Yes, it's working now.
All right. So hold on a minute. Right. So So just to give you a quick look at the block cipher, this is how block cipher look like. You have a plain text, then you have the block cipher algorithm, then you take in a single key, and you produce a cipher text. Then these are round functions. We have the same round function for each round until we, so this entire RO to Rn minus 1 is the block cipher. Yet, as we said earlier, we are actually trying to exploit the XOR difference between a pair of plain text or ciphertext. So now take a look at how it looks like. So here we have the x1 and the x2, which is a pair of our input. So we pass them through the round functions or block ciphers until in the end we will get the y1, y2, which is the output. So if we try to use the XOR between the input, a pair of input, and XOR between the pair of output, we will get the x and the y respectively. Our goal here is to use the differential cluster search algorithm to try to obtain a high probability of the x to the y. So this is our main search target, to obtain a high probability of the x to the y, which is known as the differential trio that have the input difference of dx and the output difference of dy with the probability of p. So here, our differential search scale exponentially with block sizes and number of rounds. So searching differential of block cipher with a large block sizes as well as a large number of rounds is computationally intensive. It requires more efficient technique in searching the differential. GPU provide additional processing power to aid our searching process in addition to CPU. So if we could somehow come up with the algorithm to utilize GPU, it would allow us to utilize more of the existing computing power that is available in your maybe in your data center or your processing center which have GPU cluster. Then we could use together CPU and GPU to search for our differential cluster. So this is basically what the algorithm has contributed. It shortened the computational time to search for cluster. And as a result, it should allow a more practical search for a large block size and higher number of rounds. Then it is used to obtain improved differential probability on our trifle, give, as well as present, which all of them are the block cipher of SPN structure. So it provided a basis for an improved differential K-only-2 accelerated by GPU for evaluating future ciphers. So before we go on to the real algorithm, so here we have to look at what is GPU. If you are not familiar with, you can imagine GPU as a with lot of processing unit like a small CPU inside of them. Then if you try to work on GPU, you have to of course make your work to be parallelizable or multi-threaded, massively multi-threadable, so that you can utilize the GPU processing units that are because GPU have more processing cost. So it should in a sense be more efficient than CPU in processing this massively threaded workload. So GPU memory actually divided into three parts. Or yeah, there is more, but these are the three that we are interested in or that I have used in my algorithm. Here is we have the local memory, of course. Local memory is usually also known as the global memory, but it is a local in the sense that it's different from a global in the sense that local is a scope memory. Other thread cannot actually access your memory unless you are doing some kind of wrong memory access that allow you to spare outside of your own local memory. But if you are doing the safe or more correct way of accessing memory, you should stay within your local memory. But since local and global actually reside in the same memory types, they are so by far the slowest. Of course, there is also one more memory that are not really memory but just register. So register is the fastest. Your individual thread will have all of them have their own registered memory. That depends on how you use them. But you cannot directly try to specify when to use them. It's usually done by the compiler for your CUDA, which is used in our algorithm CUDA because we are using FTAR. Then we also have Shared memory. Shared memory here actually refer to the memory that is shared among the blocks. So shared memory is significantly faster than your local and global memory, provided that these memory are not cached, but those are more detailed that are on the compiler side, so we won't cover. What is important for your shared memory is that if you know that you need a block-wide access to that data and or block-wide contribution toward that data, like you are adding up all of the thread inside the block are adding up to reduce the value, reduce your summation or to perform a summation over the block, then you can use shared memory to achieve that. Then we also have constant memory. Constant memory is especially good if you know that for sure that all of your thread will access the same memory location at the same time. So in a sense, it's a broadcast in the sense that it will be sent to all of them, which is much faster than you using local memory to cache the value. So for your typical CPU GPU flow, it will look something like this. To start, we have the host CPU program. Then after you normally in our cases for our differential cluster search, we will start with the differential algorithm search to find the first differential that we want to cluster. Then during the second part, we will send the differential with all its information and set up. We will calculate what to set up. Then you will pass all the necessary information to the GPU or copy them to the GPU memory and then initiate the kernel. Then once the kernel is launched, it will it will launch according to your specification or configuration, like how many grid to launch, how many block to launch, how many thread inside the block to launch, and so on. So after that, it will start processing your thing. Then after the algorithm is done, it should at the end have the differential result, the differential probability for that cluster. So after that, you just need to copy it out back to your host or back to the CPU, and you decide whether to keep it or to write into a file and so on. So for our autonomy search for differential, so here we are actually using the modified Masui algorithm, and it is actually just a version of partial and bound algorithms, which is specifically designed to search for trail. What it does, it improve a heuristic BN over the course of running. This BN will be used as a basis for pruning. BN here refer to the probability of your trails, best trail found. This algorithm specifically, the one that I described above, specifically used as the basis for parallelization on our GPU platform. But instead of using the BN heuristic, we actually use other heuristic. Here we used a different estimated probability heuristic, which is not the same as the BN used in the Masui algorithm. Here the probability estimated is actually quite simple. We just use for every round, we just estimate that it will be maximum 1 FTX process minus the next round. That means that the next round we'll use a different heuristic. Then for the next round, we will just directly calculate. Here, for example, we have 2 or 3 xboxes. So for example, let's see it as 3. So if in this round we have 3 xboxes, the heuristic will be for these 3 xboxes, we will take the highest probability of them. Then this probability plus the current round probability of the field will form the this round plus next round probability. Then for the remaining round probability, we will just assume that it will be the best case, 1 at the xboxes. And then we take the highest probability of that 1 at the xboxes, and then we combine them together to form our estimated probability. So it's quite different from the BN use. Then, secondly, we have the FTX process heuristic. So, because our algorithm actually required the activity to be low, so why we need the activity to be low? Because low FTX process normally means higher probability. Hold on a minute. So here we have the ATX boxes. So lower ATX boxes is better. So we try to have as low as a ATX losses as our second mounting criteria. So this definitely depends, but during my heuristic search, I found that 3 or 4 to be better in terms of obtaining the nice balance between the speed as well as the number of trail founds. So it's either 3 or 4. Initially, you can use 1 or 2, or it's normally in the case is 2. But in some cases, 1 still provide result. But for some block cipher, 1 doesn't provide result because there is no one trail through the block cipher with one active X boxes through the block cipher. So normally you can start with 2 to just filter out the differential that you think might be worth continuing to 3 and 4 at the exposures. Because once you increase the at the exposures to 3 and 4, the searching time actually increases exponentially. It increases exponentially. So before you go to 3 and 4 or even 5, if you really want it to be more than 4, but normally I found that 4 to be quite nice balance already. You can also increase it to 5 if you want. Then during also, I have to mention for the estimated probability, the algorithm that I have actually also allow you to customize the extra probability, like how many probability that we have to take, how many range of probability that we can take. For example, here maybe that our trail will be negative 64. Then I can define it up to maybe 68 or even 72, depending on what I want. So it's 4 difference or 8 difference. So this difference actually settable by the algorithm as well. So let me go to the next slide. So here we also actually using the mean in the middle approach. So we have to go through it. So it makes more sense in the code later on. So here you can see we can actually divide into 2 halves. These 2 halves. So this in our algorithm, I refer it to alpha as the first half and beta as the second half. So this is what the symbol represents. It's just the first half and the second half. So in the first half, if the algorithm is the same, we just try to differentiate and search it, and then branch until we reach the predefined round. Then we store the intermediate result to the memory. I will go through on what to store and what to not to store later on. So in our backward search, we also perform the same backward search, and then we store in the memory. So the intuition behind using MITM is usually because our algorithm searching effort increases exponentially. So it's therefore easier to search half a round than two to half of a round than to search the full rounds because of the exponential increase. Of course, it means that we have to compromise on the memory. We have a memory issue because we are trying to store the result. So it's a compromise between speed and memory. So in our specific case, we have a encoding use. Here, we actually have come up with a recommendations. So this is just a recommendations for you because we have a fixed memory slot. So it's prudent to go with just 3 most of the time because even this 4 is actually quite tight of a number for your 34 block cipher because you might need to copy out a lot of different information. One, if you copy more than one, just the probability. Maybe you can also copy out the ATX boxes and so on. You need to store them. That means that this 4 is definitely not achievable for your normal memory already, unless you have a very strong, like 64 gig graphic card. Then this still might be possible. But in my cases, I can only use 3 ATX boxes as the maximum during our mean in the middle. You still remember this is the memory. So in the memory, I can only accept those difference with an ATX boxes smaller than or equal to 3. So once you have the memories, this is how you could encode it. You just encode the positions of your, for example, you have the 1, 2, 3, 4. You have you have your processor only have 4 Xboxes. Then you first input the positions. For example, 1 will be 0, 2 will be 1, 0, and so on. So you just fill out how many bits that your position have. Then here you put in the value. So depending on what is the maximum value, you just put it in. So here maybe your value is 16 or 16, which is actually this, which is 15, 0 to 15 scale. So and so on. So for the next one is 0, 0, 0, 1, and so on. So this is how the encoding will look like if it is translated to your code in the value form. So let me go to the code that represent it. So I actually call up the code because it's quite short and it can be presented in here as well. So in here we have the index. Index here refer to how we're going to index into the memory. So we have a memory, and this is the index. So this is our index. Oops. All right, so this is our index. So here you can see we are actually doing the same thing. We're doing actually this is the index of your Xboxes. Like just now, this is 1, 2, 3, 4, or 0 to 3, depending on you start on 0 index or first index. Then we have the value here. This is a value. Then here you shift it to the corresponding places. Like the first chunk, the second chunk, the chunk is shift by this section. So this is how you obtain the index. So after you obtain the index, the indexing is straightforward. Like how you index array, you just do it. You put in the index and retrieve a value or store the value that you want. So that is how MITM in the version that I have work. So of course, this is not perfect. If you remember correctly, our ATS boxes has to be smaller than equal to 3, right? So another way to do it, to make it work to ATS boxes greater than or equal to 4, is definitely can be considered to only cache the high probability result and use a different encoding method for it. This is not attempted in my versions because I found that AATF exposures smaller than or equal to 3 actually contribute a large proportion of the probability, but it might not be the case for some block cipher. So you can also try to implement on your own on how to use the high probability result only to index and retrieve the things. The only difference will change in only the indexing part. So the rest of the algorithm will still remain the same. So this is depend on how you want to change how you index thing. So like I say, it might lead to trio with higher significant probability if depend on the block cipher structure, depend on your block cipher structure. So this is not a guarantee. So depend on whether you want to try out the high probability approach or just use the approach that I have, just index everything smaller than or equal to at the exposure with 3. Then to prepare our differential color search in our algorithm or framework, here the basic strategy for CPU only, is uses our modified Mouse-Wheel algorithm with the AS and the estimated probability to find the differential trio suitable enough to be served as the starting point to be cluster. Then once you found the starting point, with the starting point, you populate the field. I will show it later. Then you just launch the GPU kernel. So let me go to the next slide. So here, I'm going to go through the overview of the GPU framework so you can actually get a rough idea. So for the GPU framework, here, the general idea is that we parallelize everything and we perform it level by level. So we parallelize it and we work on it simultaneously. Here, for example, we have 7 of them. So for the first one, we work on 7 of them. And for the second one, we work on 7 of them as well. But I will go to the next slide, which should be much more clearer. So here we have the full parallelization is achieved for each branch level by assigning precisely one unique virtual threads to handle every single differential branch. So here, for example, let's take for example our GT, which is our real GPU thread. GT is our real GPU thread. Then at our first level, L1, you can see that there is 7 branches, right? We have 1, 2, 3, 4, 5, 6, 7 branches. Then our G3 will process these 7 branches simultaneously in a single loop or single execution loop. Then for our next level, we actually have, if we consider that each now level 1 branches, all of them have 7 branches as well. So total up they will have 47 branches. But since we only have 7 threads, we only can process 7 of them as one. So we will go ahead and process 7 of them as well. And then process 7 of them in the next execution loop. So this is on how the GPU framework will generally work on a simplified level. So, but we will run into problem. What happens if we have a lot of, for example, in our previous slide, we have lot of threads, but we only have a few GPU threads. That means that we need to a lot of at least 49 threads to process it in one cycle. We need to process it. Hold on a minute. All right, so let me see. There's some problem. We have a problem for Y Kong just now. So maybe I'll stop here for a moment to address the problem first. All right, you are not sure what work performed on the GPU, right? It performed everything on the differential search. So hold on a minute. I still have a lot to go through. So maybe I'll answer what is the difference between CPU and GPU. I believe you are asking what is the differential of performing the computation on CPU and GPU, right? So they are actually different structure. So for GPU, you are mainly on working with to achieve the performance on GPU. You have a lot thing to optimize for. We will cover that later. For CPU, all you need to do is just at least in our differential cluster search case, to achieve the ideal throughput, you can just use different starting point. Like you have a first dx1 to dx1, then you have the second dx2 to dx2, right? So you can just have the threads of different CPU to work on different dx and dy. But for CPU, but for our GPU, in our case, this is not achievable for a lot of different reasons. We'll go through that in a later slide as well. So let me now first finish up the part on how the GT and T work here. So what I'm trying to say before it is that during our L2 levels here, before we can go to L2, there's actually 49 of those branches, but we only have 7 threads. But let's just say that we cannot just look through the rest of the branches because our memory is limited to store the result for your 7 branches only. So it can only store 7 branches only. So definitely you cannot just go through it and ignore the rest because it only be stored for 7 branches. So you cannot just go through the rest of your bottom branches already result already disappear because it only can only store for maybe 7 to 8 branches at a time. So what I have here is the top level view on how it can be solved. So we do them in a sort of a GPU recursion loop. I will show how it works in the real implementation later. But the general idea is that we do it in a recursion loop in the sense that first you have all of the branches. Let's assign all of the branches to work by a virtual thread. So we will assign them to a virtual thread first. T1, T2, T4, T4, this is a virtual thread. Then we assign those virtual thread back to our real thread, GT. So this at the end, they will work on this virtual thread. For example, GT1 will work on T1, T2, T3, T4. And for GT2, we will work on T6, T7, T8, and so on. So these virtual threads, like I said earlier, we only have limited memory, right? So how do we group those execution together so that it executed as a group? So that is more systematically executed as a group, and we can track on how far we are when you are coming back to execute the remaining branches. So here we actually assign each mu here, small u mu, is our one loop of executions. Means that this loop of execution will perform the entire branches processes from selections, branches, bounding, and pruning, the entire process of branch and bound in one loop of executions. Then after you perform this one of executions, you can go on and perform the next until we hit our memory limit, which is usually denoted as the length of m. Once the length of m small u execution unit have been executed, which means that we have reached the fixed memory limit for that particular level, which is m1, then we have to go to the next level. So it will go to the next level until we reach the end, and then it will go back up to execute the second part of the unit, which is M2 of the second last level, before it coming back up until your first level and execute the second M2 of your first level. So it happens recursively. So by doing this, we can make use of we can basically solve the limited memory of our GPU and basically solve the differential cluster search, because the differential cluster search is actually in the unit of maybe billion, or even trillions branches, and the memory explode very fast, very quickly for our exponential workload. So by using this recursion-based loop of execution divisions, we actually can use a limited amount of memory to execute the entire thing. So this is basically how I approach the limited memory of GPU for executing the entire thing without going back to the GPU, the entire algorithm of differential cluster search inside GPU. So this is the main thing to be solved. So to overcome this, there is a lot of implementation details as well that we will need to talk about if we have time later. So let me go to the next slide first. So in practice, the thing is that even though we define that each level executed simultaneously together, but in practice, because of the memory limitation issue, we have to execute them in bunches. So here, maybe for example, the first bunches we execute 4, then second bunches we execute 4 as well. Here you can see for each level we have 2 branches. The top level we have 2 branches. Two here also have 2 branches. So this is the second part we execute this. So for the third part, we also execute 4 branches. You can see 1, 2, 3, 4, the 3 part. Because this is quite different from the top, because this is the end node. This is the end node. We don't need to do branches, so we can visit them and directly solve them. So you can say that they have the branch number of 1. So that you can see it kind of have branch of number of 1, so they count as 1 instead of this, which has a branch number of 2. So here 4, you can see we do the 4 in here as well as here. It's split across different nodes as well. So in our actual implementations, we just dump them all together in an array. And then we use calculation indexing to calculate which part of the thing they are at to perform the corresponding differential cluster search or differential branching on them. So this is also another index approach. using implicit separations by doing our calculations. So I will show the calculation in a minute. Let me check the chat first. Right, so here we have the GPU accelerated branch and bound algorithm. So this might look quite confusing at first, but I will work through it slowly. So as we said earlier in the previous slide, here we have we need the index, right? We need the index to know that which node that we need to address, because all of our node in our memory is just a huge chunk of array. So to know that which node we need to retrieve or which node we stop at, we need to refer back to here. This is the part on how we calculate the node positions, part of the calculation needed. So here we will actually calculate on what is the number of branches. This is actually a number of branches. For that particular node. And here, because we actually treat them as a together, so we also have to make sure we treat have the lineage of the previous one, so that we know exactly where to begin and exactly where to stop as well. So here, the entire idea is that we need to know every single one of the number of branches for every single node, and then we add them in a stack summations manner. Then, once we have this information on the number of branches for each node, then only then we can index it directly through the use of a sort of a different number system. For example, here we have different Xboxes. Maybe let's take the example from earlier. 1, 2, 3, 4. We have 4 Xboxes. Then for each Xboxes, right, we have different active Xboxes. So maybe it will be 7, 8, 9, or even 2. So this is the AS number. Then because the number of branches for this particular combination of Xboxes is actually 7 times 8 times 9 times 2. So this is how many different combinations they could have. So to know exactly which, and each of these combination is actually directly executed by one virtual thread, or you are assigning them to one virtual thread. So you need to know that to calculate the virtual thread ID, so that we know that which thread to assign this virtual thread to, or this workload to. So to do that, what you can do is just use the standard one. For example, you have, for example, maybe you want the 9, I believe is a 8 one. You want to the 8 item in the combinations. So what you do is it is actually 1 0 1 1 0 0 as the index. So this is an index for that particular ATX boxes. But we also have to consider the others Xboxes as well, or the others differential as well. So in the end, we actually have to consider everything. So this basically what it means by this, because we not only have these combinations, we also have the previous one. Maybe the previous at the Xboxes is two Xboxes with different branches like 8, 2, and so on. So what it does is it allows you to index directly to the correct thread ID once you know the number of branches for your ATX boxes. So here is just how it works in practice. You actually have to use modulo the number of branches to know that which ATX boxes to differentiate to. For example, here we have four Xboxes, right? Then what you can do is you just know the number of branches that this whole part, which is seems quite complicated, but what it means is that we need to, since we have the entire number of branches together as well as the previous number of branches together, we have to try to calculate the current number of active branches only, depending on the number of threads before it. Then we try to modulo the number of branches now to get the correct number of index that need to be input in this. to directly branch into that particular branch for this particular thread ID. So it's actually quite a bit complicated than the rest. But if you work through the thing yourself, or you work through the simpler version that I have, not from this paper, but the previous one, then it will be maybe more intuitive than this one because this one we have bundling issue. That's why it's more complicated than the one that don't have bundling issue. We just assume that it is. We don't need to consider other differential, other different branches. So this we have to consider other different branches. That's why it look more complicated. But the main idea is that we have the number of active branches, and we can somehow use the modular function so that we can directly get the index that we need to index correctly to the specific branches in our differential distribution table. So this is what the entire thing is about. So here we have the few issues that I think need to go through at least briefly. So if you are going to use our differential cluster search algorithm to search multiple differential in quick succession, especially those that complete within milliseconds, you try not to reallocate memory. Just use them because reallocating this much memory because of my algorithm actually uses a lot of memory. We try to use the maximum amount of memory available and divide them between individual rounds as well as individual threads. So just try to reuse them instead of reallocating them. You can try to mem set them instead to 0. If you feel that there might be some error there, you can just, when you're going through, just mem set them to 0 to reset them to the previous condition before you start the program and re-execute the differential algorithm again, cluster algorithm again. So other thing that is more specific to GPU that I think I need to cover as well is you have to minimize the if else branches because of the something called as branch diversion. So branch diversion is that because the GPU comes in execution unit of 32 watt for CUDA, I believe this is the 32 is number, CUDA watt. Since it's the case, that means that because it's based on SIMT structure, right? If you know what is SIMT, it means that all of the process will execute on the same different data, but execute on the same instructions. So it's almost similar to the case with the GPU, since it's based on SIMT architecture. So you have to make sure that every single branch are executing the same instructions as much as possible. So just minimize the if else branch or any condition branch that you might think that the GPU will branch depending on their instructions and condition. The if else branch is the branch to avoid for each branch is the branch that execute different instructions. Or you have if you just check for some conditions, if you just check some conditions, and after evaluation of the conditions, all of the branches will have the same conditions or same evaluations. That means that this is actually not branch divergent because well they execute the same branches. So that is part for our branch diversion to look out for. Also, we have to maximize the GPU occupancy. Here have the GPU CUDA have a very nice tool for you to optimize the occupancy. So here, if you boot up the one that found here, the Excel file found here, you will see a bunch of these. What you can do is you can select based on your compute capability and the CUDA version as well as the shared memory size. This can be retrieved from your GPU. You can just refer to the example as if you install CUDA, in your CUDA installation, there will be some example that teach you exactly how you could use code to retrieve this version, these informations. Then you also has to input how much you use. So this is a part that you can customize how much you use. So basically, what your objective is you to tweak this or based on what is suggested to tweak until you have the occupancy to be 100% for each SM. At least that is the objective. Normally, if you have too low of a occupancy, your overall performance will suffer as well. So try to keep in a number as high as possible. This one by tweaking this one based on your SAT informations. So here it will actually tell you on how you could tweak it. So this is how you could use the Excel file to tweak your thing. But you not just need to tweak in the Excel file as well. If after you tweak it, you make sure that your code actually conform to these specifications. That is how you get the occupancy, not by directly tweaking the Excel file, but tweaking the parameter in your code. So one last thing is that to get the good performance, you have no choice but actually to use an Nsight compute to help you profile your code and to see what part of your code is struggling. For example, in my case, my code previously also struggled, if I remember correctly, with the most of my code actually spending too much time on fetching memory. So I have to address that as well. So in your part, it might be different. Maybe you are compute bounded instead of memory bounded. But if you're memory bounded, you need to do more thing as well. If you are if your compute is too low, that means that maybe you are not having enough data to compute as well, or your memory too slow. So there can be a variety of reasons. So to get a more detailed reason on why is the case, just do the Nsight compute. You can consult the official documentation on how to do it. So the base main thing is that you have the program, then you run through the program through these two, then it will generate a report like this. Then there is a lot of details report here. So here we have the theoretical occupancy and achieved occupancy. So I have about I think 100 on the theoretical, but my achieve is only about 80 or 90 as well because of some of the bottleneck of my memory issue. So you can go through it yourself to know which part you need to improve on for your own specific use. So with that said, if you are totally new to GPU programming, this is how you could, and you wish to implement my algorithms or to modify my algorithm yourself. This is how I advise you to start. You can start on playing with the dummy program first for adding up maybe the simplest program for adding a number in the array to reduce them to a final number. The main objective to do that is to familiarize with the CUDA syntax because it's quite different from your usual C++. Because of the syntax is similar, but the function is actually quite a lot of CUDA specific functions that you need to be aware of to actually implement it. Then you have to know how to you allocate memory, how you free allocate memory, and in general, what are the type of memory. So we try to experiment with it and try to benchmark it, whether when you use share memory, whether you use broadcast memory, or you just use a normal register, which is faster. So if you don't want your variable to remain in register, you can actually split it up by a specific command, but I forget the commands. So you can look it up in your official documentation when you're messing around with memory. Then you also have to familiar with how much grid, what is block, what is thread, and how do you define them, and so on. So all of this is the objective of creating dummy versions. Don't just create a dummy version and or it work, then you don't experiment with this. You try to experiment with this so that you know how it work. Then as well, you try to familiarize yourself in how Nsight compute work to identify bottleneck for optimizing your first program. And you also have a rough idea of how GPU thread works, especially if you are new to parallelizations. Parallelizations. If you have not worked with any thread before for parallel computing, you might you might want to start there first before you go to GPU, so that you don't have to worry about the parallel aspect of the GPU more, or you worry about that less. Then just create more program to practice if you feel it's necessary to get a hold of this. Then after that, what you do before you actually go through the more advanced versions, I highly recommend to go through the automated search for SC paper, which are actually using only one round differential search, which means that in one round, I will send the data to our GPU, then it will feedback, and then in our second round, the CPU will do the selection again, and then it will send each selection to GPU, feedback the final result. So this is more simpler in the sense that I only process one round of small dx to dy, one round only, and one round and only one So it's basically much easier to understand than what I have here. I have a lot of thing to check, a lot of thing to prepare because of the recursions. Then finally, once you actually know how to do it, you can try to implement it. This is actually more simpler or much more simpler than what I have here in the second one. If you can implement it successfully, then you can go on and read the optimized versions that actually uses bundling to address the issue that exists in the AC paper. So, so these are the link for the papers, the ePrint for the two paper. This is the earlier version, which is a simpler one, and the later version is a more complex one. So that is basically it. But I think I have to show the code or answer the questions. Maybe I answer the question first before I show some code on how you could maybe modify the code. Maybe I will share the code from quickly go through the code with you all. Let me see. So for those who are actually want to modify the code, so all right. So for common, it's just a very common functions. You don't really need to modify anything in here to get the thing you need, unless you have a differential tables. You maybe has a 16-bit differential Xboxes and so on. Yes, yes. We can give out the slide as well. So before that, let me see in here, right? So here there is something that you can modify. For example, trap a block number. So this I try to be as descriptive as possible during my code. So maximum Xbox. These are all you can think you can modify. So this is a pattern round and material forward. Pattern round. Pattern round is a very bad name. Um, I don't know why I give the name of pattern, but it's actually the round MITM forward. So just ignore the pattern. It's actually now MITM forward or MITM forward now. So this max branch per round. This is the number of max branch that I have calculated that I think kind of okay to use. So you can change it if you want, depending on the size of your code. And this is just the remaining header. You don't really need to change anything here if you want to use it. So let me go to the rest first before we go to the main GPU. Here there is not absolutely nothing to change for the main. Yeah, it's just to initiate my true code. Then here is the part that main refer to. Let me go through it first. This is 100% accurate in terms, not 100% accurate because it doesn't really take into account most of the trails as well. But it is actually exact method, heuristically exact method to get the probability. So if you change the probability to ATX boxes, that means you only add in the ATX boxes, it will be accurate. This is not guess. This is actually trying to go through the concrete path, then try to sound out the probability. So if you just change the probability to X boxes, then it will just sound out the concrete X boxes along the way. Contributor or modern console. Um, I'm not familiar with those, but I only know that they have more ray tracing because they have the things like the matrix multiplications. So those are specific hardware that is good for ray tracing that I didn't use because I don't have it. Yes, this is not as this is not dynamic parallelisms because I feel that dynamic parallelism have the issue with that level as well. This is a recursion. Let me show you. This is actually using what is known as the, I believe it's known as the group barrier. Let me show you on the actual thing first. Here the forward and backward. All right. So here All right, so here is the real GPU code. All right, maybe I got disconnected just now. So about the dynamic parallelisms, you can try it. There is no harm, but I feel that the depth issue of your what is called the dynamic parallelisms might be an issue here because we are actually going through high number of round, and then even if you do dynamic parallelism, I'm afraid the memory issue will still be an issue. You can definitely try that, but for me the what is called the recursions using the dynamic, not the dynamic, the group barrier, in the sense that I in net here let me show you where I do it. So all right, so let me show you around here. Here is the part where I after I do the all the permutation and so on, and I calculate everything and say save it. Where is it? Let me minimize everything first so I can see my function. So is it this one? Oh, wait a minute, did I open up the wrong slide? Or maybe I open up the wrong. Maybe I will just open a GitHub versions. Easier. I get the wrong folder already. Yep, I downloaded the wrong folder. I'm sorry about that. So maybe I will share the GitHub versions better. And how do I let me share the my browser? So after I do everything here, if you see my browser, I believe you see. So this is the part of after I done everything and I permutate and I save and prune and so on. Then this is the checking part where I have to add everything together, store everything together, and then I do the grid sync to sync for the grid before I go on and I add everything together here. So basically this is the part where I actually do the what enable the recursion to happen. So I forgot what is this called, but I believe it's called cooperative group. So I use the cooperative group things instead of dynamic parallelism because I believe that dynamic parallelisms actually might not work, but you can definitely try it. I have no guarantee that it will work because of the memory size as well as just how the branching is totally not predictable and so on. Can definitely try it. I don't know whether it will succeed or not. All right, so here we have the to change the differential table. You just change it here and change it here. So you have the forward one and the backward one. Make sure you change both of them to make it work. Then here I believe you don't need to change the pose, but you can just change it. Just those will be safe because some of these I left in because of the compatibility issue. But just change everything according to their name. So this is the differential table host reverse. Post here actually means the CPU code that used by CPU. But just to be safe, just change everything accordingly. So for differential table without the reverse name, that means the forward differential table. Then with the reverse name, you put in the reverse table. Then for the probability, it just change the probability here. Then frequency, change it as well. Frequency here refer to the how you obtain the probability. So this is a frequency, just calculate it accordingly and replace the frequency as well. So here the differential table size actually refer to how many differential that particular branch how many branch that particular differential have. So here the first one, because it's on 0 0, will only go to 0 0 100%, so it's one. Then for the other, there's basically 7 branches, so I put 7 7 7 7 at least for trifold. For present others, these 7 7 will not be the same. It will be maybe 3 4 6 7 3 4 4 6 8 and so on, depending on your table. Then here the reverse is after you perform the reverse of your table, then you also try to calculate the size of how many branches on particular dx to dy will have. So the whole thing is the same. It's just in the CPU part. Then this is the place where you change the dy dx. Then this is the initializations where you do all of the malloc allocations, memory allocations, and memset. After you've done the memory allocations, then this is the part where you basically the algorithm. So here is just a copy to the table, and you just wait for everyone in the thread to everyone in the block to complete the copy, and then you continue. Because this is the part where shared memory is used, so we have to make sure the shared memory is properly initiated for the block. Then here is a lot more initiations. Here is I do this because I do this instead of making them memory because of the register limit issue that I have. To achieve a theoretical occupancy 100%, I have to use less register or spill those register to local memory or global memory. So basically, I do this so that it's actually calculated every time instead of storing in a variable or register in this case. So I do this just to have a lower register count. You might try to experiment with this as well, but what I found is that by doing this, I achieve higher performance because of the lower register, and I can achieve theoretical occupancy 100. You might have a different case depending on the exact model of your GPU and how you optimize the rest of your things. So this is why I do this. Why you think that why you are doing this, not putting them in variable and let them cache in the register. So this is why I want to reduce the register use. So this is, even though I do this, there is no 100% that the compiler will actually do at one. So it already totally depends on the compiler as well. So here, just because I use as a recursion and my condition actually quite complex, so I just use the condition checking later on to break out of the loop. So here you probably no need to change anything. The thing that you change is at the top part. Here is how I do it, how I do the algorithm, whereby I try to initiate and calculate the everything required, like the total branch for that particular level that I show you the very complex equation thingy. So this is all part of this. Then here we find the correct dx by using the block level. We go from block level to grid level. I mean from thread level to block level to grid level. Yeah, tree level. So you will search from the block level first, then you will go to the thread level before going inside the thread level to see which part of it is. So I do this because of the dx. I don't know where the dx. I have to find it. That's why I have to have all the size to know which part to find. But it's a lot of finding. Here I forget to mention that I use this linear find because my thing is not sorted. So I only use a linear find. You might find that binary search might work, But what I experienced with is I obtain no difference, and my binary search is actually quite complex as well. So you have to experience it on your own. But here I only use linear search and it still works quite well, so I stick with it. So after everything, you will find the correct dx pointer, which means I found the correct ti that I need to be, or the correct ti for that particular branches need to be. Then I just go and perform the this is this part is the part where I talk about how to use the modular to get the correct index into different branches. Is this part. Then after that, it's just a straightforward permutations and do the MITM part. And then after that, I need to basically add up all of the number again, all of the thread number again to prepare for the next round. Then here is the part where I have to do basically here is additional checking, but I don't know whether this is necessary or not. So you might want to experiment with this. So here is the part there where I do a checking and specific updating condition, and then I do here is a part where the recursion happen, or is the part where recursion is can happen because we uses a cooperative group singing. Cooperative group is a newer feature the older model don't have. It's even newer, I believe it's even newer than the dynamic parallelisms. So this is the part where I told everyone to wait up until everyone finish up their jobs for every thread. So before they continue, and the rest is just straightforward checking, and then more checking to ensure everything work. So I can see the actual algorithm, the complex part is definitely the checking part. There's a lot of condition for the thing to work, and a lot of thing to check, and a lot of thing to prepare, just so that we can perform the modular, as well as find the correct DX to branch to. So the important part, if you don't want to mess with this, is just using the same structure to change the differential table, as well as the permutation. If you have the same 64 structure and 81 and 28 bit structure. So is there questions? So I believe I didn't address the memory issue for Wai Kang. So I didn't during the entire process, GPU process, I didn't do any read or write to the global from the CPU to the global memory. So that part is definitely not an issue. If you are talking about during the part where I'm writing or reading from the global memory, so maybe you can also do the coalesce read or write to further improve the performance if you want. But there is no guarantee that it will improve a lot. Since I believe the main thing about my performance bottleneck is about the time to wait for the thing to fetch the memory. So you might have a different case. You can definitely try to improve it. This is by no means perfect, but it is definitely good enough as to show that it's actually faster than CPU approach, as well as more economically feasible than the CPU approach. So to basically launch my code, you just need to type the build.sh here I have. Here are the build script. Oh yeah, very simple build script. So here you have to change your SM number based on your SM versions. You have to change it based on your SM versions. So my version is 61. So to get the SM version, you can look up the internet or use the thing that provided by the CUDA to get your own SM versions. Depending on your card, but you have to change it to, or you can just add more to so that it compile to your versions. So this is the important line. I believe. So the rest is not that important unless you want to do the performance checking and debugging. Is there any more questions? Also, I believe I also need to answer your second part of the question about you are searching at many level of a tree. So here is actually searching at one level of tree at a time before we move on to the next level, because the tree is so large that you even if you try, you cannot complete one level except for the first few rounds. So you will have to move on to the next level using the recursion method that I have and try to fix the amount of memory each level should take up in cache, so that by the time I go back to the first level, I still have what I need to continue to the next part of the searching. Maybe I will go through the part on the linear search. So long is quite complex, but it's just the way to search to know which part we need to basically index into. So this from the top to the bottom is actually the entire kernel differential. Once you input the dx and the rest of the preparation value as well as the dy, it will actually perform the entire differentials from round 1 to round maybe 21 or 22 or even 23, and do the both the backward 24 forward 22 20 something round until backward 20 something round, so that everything is okay. So in the sense that this once you launch this just you can in practice, if you try to launch the algorithm, what it will behave like is you can imagine that it's like a very it's like a CPU approach as well. So to achieve the distributed computing approach or heterogeneous computing approach, you can just compute directly the dx dy for every single what is it called, for every single thing that you want. For example, you can go through the Matsui algorithm first to have a list of the differential that you think you need to go through to for different cluster. Then you can split the work between CPU and GPU, and the scaling should be linear in the sense that as long as you have enough differential for each of them to search, then the speed up will be linear, and it will be optimal basically. So wait a minute. Maybe I will show on how you could modify a bit. Let me see. Mm, and let me open up my Windows. um, because I don't have the Google server in my place anymore, but I will just show you the general idea on how you can launch it in the Google Cloud. So I have to share back my screen first. So basically, once you go through the Google Cloud platforms, you just need to go to the compute engine, go to the navigation menu, go to the compute engine, click on it, then click on create. Then in here, select the thing that you want. You can select US is no problem, but Taiwan will have a lower latency when you are actually using SSH to remote connect to the machine. So select the one that have the GPU. Let me see which one has the GPU first. Hmm, which the one that has GPU again? Let me see here. Maybe we'll just stick to US for now. So this is where you should add the GPU, but for some reason it's not showing up for me. Do I still have the template? Let me see. Before I had to have a template for it. Yep, I have the template now. So here you can see I have the template which I use for my experiment. So you can use the same template or you can change to Taiwan. Taiwan I also use for one template, but I don't have the template anymore. So I can only show you the US one. So here I have the template. I just select US Central 1 and the zone. Some of the zone don't have the GPU I need. I believe this has all of the GPU that I used the experiment on. So depending on what you need, you can select the GPU. Maybe you need P4, you can select P4, which is the one that is cheaper. And since it's cheaper, this is more cost efficient, but it will be slightly slower. But if you try to differentiate a lot of differential, that means that T4, P100, and so on will be much more less cost effective than using P4 because P4 is the cheapest and the performance doesn't really degrade that much when you downgrade. So depend on your personally. It's just recommend to do P4 just because of the sheer um, cost efficiency of the GPU lah. So after you select everything, here you don't really need the display device, and the here you can select the distro that you are familiar with. Basically, you can select the one that with your CUDA 10 installed, or you can if you don't select the one with CUDA 10 installed, just install the CUDA 10 yourself, or CUDA 11, I believe the newer version. I'm not really sure. So here you can select Ubuntu if you are familiar with Ubuntu, or you can select Windows if you are fine working with PowerShell and so on. So just select the thing you want, the show you want, and then click create, and it will create the distro. Maybe I will create, see if it still work. Also another thing is, if it's your first time using the basically the Google Cloud thing, the thing is that you have to basically, I believe is it to email, you have to do the basically you have to request for additional GPU usage. This is not enabled by default. Once you try to initiate it, it will say that it fails on. I believe I was success because I already requested unless they revoke my permission again. So if you fails, then it will show that something you don't have GPU 0 or something in the region. So you have to go to your setting and try to request for more GPU. So you can look up in the official documentation on how to request it. So once you have it, you can just start it up, then use the normal SSH and so on to connect to it, and then copy the entire file to the Google Cloud, and then just do it. But let me check whether I still have the script so that I can show you how it works. I believe I don't have the script anymore, but basically it's just using SSH and just copy the file into it. Then you can basically successfully launch it and use it, and copy back the result if you need. So is that question regarding the Google Cloud? You can also try to use the interface that's available here. I believe it still work. But I never tried it before. I just use my terminal to connect to the thing myself instead of using the terminal that is provided here. So I'm not and cannot guide you on this. You have to explore on your own if you want to use the in browser terminal. So I believe that these are you guys. Do you have any more questions? If there are no questions, then thank you for coming, and I basically share the main thing about my paper already and my GPU algorithms main things. So I will pass back to the dev for the remaining speech.
Okay, thank you very much, Weiju, for your sharing session. So I hope that everyone found it interesting, and hopefully you can apply it in your work, or even if you're working on block cipher analysis. And for those students under my supervision, hopefully you can take this has been useful. And if you have any questions, I think you can still contact Mr. Yeoh to address any of your concerns. So if there are no other questions, I think we can end the session, and I will upload this video on YouTube, and I will share it with everyone just in case anyone wants to go back and look at which parts of the codes need to be modified and so on. So thank you again for attending this webinar. I know it's a little bit of an ad hoc webinar. Actually, originally it was meant for only students under my supervision. So thank you very much again, and hopefully we'll see you in any future webinars.